etale cohomology of adic spaces as in yesterday, let X be an analytic adic space. So as in the case of schemes, first we define the etale site on this X and consider sheaves on that site and take a cohomology. So it's completely analogous to the case of schemes. So let X be an etale, we denote X at the etale site of X. Namely, it is a category with topology. So as a category, it is X at is a category of etale morphism from some adic space to X. And of course the morphism between two objects are morphisms over X. Morphism is morphism over X. Namely, if we have two objects in this category, then the morphism between this and this it is y and y prime, and base is X, and this is etale and this is etale. The morphism from here to here is morphism of adic spaces such that this diagram commutes. And in this case, this morphism is automatically etale. And X is also equipped with topology, namely the notion of covering is determined, is given. So the morphism, the covering in this site is a family of morphisms like this. This is a family of morphisms in X at. So we have structure morphisms and commutative diagram, and it is said to be a covering if the union y is the union of the image of y alpha under this morphism. Because f alpha is etale and etale morphism is open map, this is an open subset of y. This is the definition of covering. This is a good point of adic space. One of the good points of adic space. So if you use classical theory to define the etale cohomology, you should suppose more conditions called some admissible covering or something. But in the theory of adic space, we only assume that it is a covering of y theoretically. Yes. And next, I will define the etale sheaf. I will define the notion of etale sheaves. In this talk, I will only consider the sheaf of sets. So I sometimes omit the word abelian. So abelian sheaf on x at is a contravariant functor f from x at to ab, which denotes the category of abelian groups. Such that satisfying the condition of sheaves. So, namely, for every covering y alpha 2y, then we have the following exact sequence: fy to fy alpha to alpha beta f y alpha cross y beta is exact. It is a kind of patching condition. So the claim that this is exact means that, so if you are given section locally, namely the element over here, and they patches in the intersection of y alpha. The intersection is a fiber product, and if we pull back these sections to intersection, then they agree. Then they patch together to give a section on y. This is uniquely, and the patching is unique. So this is the usual condition of sheaves. Yes, and here the fiber product appears. So I don't know whether the fiber product exists for every tuple of adic spaces, but at least fiber product fiber product, this exists at least if x to s is locally of finite type. So we can make a fiber product of this form. So by the general theory of Grothendieck, the category of abelian sheaves is abelian category with enough injectives. So we have operation of sheavification, and any objects can be embedded into injective sheaf. So by using the general machinery of derived functor, we can construct the right derived functor. Right derived functor of the functor of global section, namely the section of the identity morphism. Yes, the right derived functor can be defined as false. So if we are given an abelian heap on x set, then take an injective resolution of it. Injective resolution, namely the exact sequence such that this consists of injective heaps. And R gamma xf to be the complex which is obtained by applying the functor gamma to this complex x I dot. It is an object of the derived category of etale heaps, abelian etale heaps over x. And it is independent of the choice of injective resolution because it is unique up to homotopy. Okay, this is a derived category. And as usual, the ith cohomology of this complex is written by HIXF. It is the ith cohomology of R gamma XF. It is the usual cohomology. This is the ith etale cohomology of x with quotient f. Okay. We can also define inverse image functor and derived push forward functor RF lower star and its ith cohomology if we are given a morphism of adic space from x to y. So we can pull back and we can push forward. This is a part of general theory of toposes by Grothendieck. And the construction is exactly similar to those for heaps on topological space. So I don't explain it. So the definition of etale cohomology is very simple and very easy. But the problem is how can we compute this cohomology? It is a very difficult problem. So this injective, we cannot expect to construct this injective resolution explicitly. So we cannot compute it by using this definition. So even in the case of schemes, we have many tasks to compute them. But so the question is, how can we compute etale cohomology of adic spaces? The main tool to compute it is the forward nearby cycles functor. So forward nearby cycles, which I will introduce later, and the comparison theorem with the theory of schemes. So we can use the theory of schemes to compute the etale cohomology of Artic spaces. So next, I will introduce the formal nearby cycles. It is a very important tool yes? Yes. Exactly similar to the case of schemes. So this is a formal scheme version of the usual nearby cycle functor for schemes. So first I will record the nearby cycle functor for schemes. It is also a powerful tool to study the bad reduction of schemes over complete discrete variation ring, such as periodic integer ring. So let V be a complete discrete variation ring with separably closed residue field. More generally, we can consider that V is a strict Hengelian discrete variation ring, but so we don't need the completeness, but only we need the Hengelian that it is Hengelian, and let K be a fraction field of V, and put S equal to spec V. And we denote K bar by K bar the separable closure of K. Then we have the following diagram. So S is a spec V, and there is a closure point, the unique closure point of S, which is the spectrum of separably closed field. And we have a unique point of S, which is spec K, and eta bar is spec K bar. We have such commutative diagram. The diagram is too large. And this diagram is actually has actually a classical analog. So I will write a classical analog. The classical analog of that diagram is the following. First, it is well known that the spectrum of complete discrete variation ring is analog of some small disk, small complex disk. And of course the closure point corresponds to the origin, the center of this disk. Classical means the theory over C. So this is the origin. And the spec K corresponds to the punctured disk. And eta bar corresponds to the universal cover of the punctured disk. This is a classical analog of that diagram. And this is, of course, contractive. So there is no monodromy on this space, but this space has a non-trivial fundamental group. So the family on this punctured disk has a monodromy. Okay? Which one? Oh, that one? Yes, exponential. So for a scheme X over S, we can make a diagram over this XS, 2X, 2X eta, and X eta bar. So we can make such a diagram. And we denote this morphism by I, and this morphism by J, and this morphism by pi, and this by J bar. Now we can define the nearby cycle functor for a sheaf, of course, etale sheaf, abelian etale sheaf on X eta, we put R psi F to be this one. And we call it the nearby cycle functor, or a nearby cycle complex. Okay? We are given a sheaf on this genetic fiber, and first pull back it to the universal cover, the base change of the universal cover, base change to the universal cover, and push forward by this map, and pull back by this closed immersion. This is a definition of nearby cycle complex. So what is it? So classically it is introduced it is introduced to study a monodromy action on the cohomology. So there is well-known Picard-Lefschetz formula and so on. But today I don't explain about the monodromy, but I give some basic properties on this functor. First, the most fundamental, most basic case. So consider the case X is equal to S. Namely, the scheme is in some sense trivial. Then what is this functor? In this case, this functor is a stock of F. So we identify the so in this case sorry, I forgot to mention that this is object of the derived category of XS. So we have a complex on the special fiber. So if X is equal to S, then XS is equal to the closure point. So the sheaves on closure points correspond to abelian group by taking stock. And under this identification, R psi F is equal to the stock of F at the geometric point eta bar. So So this is an easy exercise on the functors. So I will give some proof on it. So recall that this is identified with the Avian group by taking stock or global section. So we want to know the global section of this complex. So we want to know this one, and we want to prove that it is equal to this. But this is equal to the stock of R psi f, and then by the definition of R psi f, we have this is Rj under rho star pi upper star f s. And because we assume that f is strict local, the stock is equal to the section. Namely, it is equal to R gamma s Rj rho star pi upper star f. And it is clearly pushed further and taking global section is equal to the global section of this one. Oh, sorry, I forgot bar. So we have a cohomology global section on this eta bar and pi upper star f, and it is equal to the stock of f eta bar. Okay. This is the easiest case. Next, assume that we are given a morphism from x to y over s. And assume that f is proper and large f, the sheaf, is torsion. Then the push forward by f and taking nearby circle commutes. Namely, the natural morphism from this one to this one is isomorphism. Here we indicate x and y here to distinct to make it clear where we consider this functor. This is an immediate consequence of proper base change theorem. Proper base change says that the push forward by proper morphism commutes with pullback functor. So we can commute push forward and this pullback. And this is push forward, so it commutes with push forward. And this is pullback by etale morphism, by end-etale morphism, so it clearly commutes with push forward. So this functor commutes with push forward. Okay. So now let us assume that y is equal to s. So consider put y is equal to s, and use property 1. Then what does it mean? So then if x to s is proper, then the left hand side is, what is the left hand side? This is push forward to the closure point. So closure geometric point. So it is the left hand side gives a cohomology of the special fiber. So I omit this again. And the what is the right hand side? Now y is equal to s, so the right hand side is the stroke of this push forward, which is isomorphic to the cohomology of the genic fiber. So if x is proper over s, then the cohomology of nearby cycle complex is isomorphic to the cohomology of genic fiber. This is one of the most important property of nearby cycle functor. Okay, so this is very important. So I want to stress it again. So cohomology, under the properness. So cohomology of R psi is equal to the cohomology of generic fiber. So it is very important.
In more precise geometric generic fiber.
Yeah. So if we want to consider the cohomology of, say, the Shimura variety, then the Shimura, we are interested in the cohomology of Shimura variety, cohomology of the geometric genic fiber of integral model of Shimura variety. So to study the Shimura variety, we can use some so on the other hand, this corresponds to the reduction. XS is a special fiber of the integral model of Shimura variety or modular curve. So we can use bad reduction or mod P reduction to study some cohomology of Shimura variety. Yeah. So thirdly, so in the diagram above, assume that f is smooth, and moreover assume that f is 0 over nz sheaf, where n is an integer invertible in S. Namely, n is prime to the characteristic of the residue field of V. Then the pullback and the nearby cycle functor commutes. Cool. This is the sheaf over Y. Then the pullback and the nearby cycle functor commutes like this. This is an easy consequence of so-called smooth base change. Smooth base change theorem says that if f is smooth, then the pullback by f commutes with any push forward, which is not necessarily proper, of course. Then again, this is pullback, so this is compatible with pullback, of course. And this is push forward, so it is compatible with smooth pullback. And this is pullback, so it is compatible with pullback. So this functor commutes with pullback functor. Again, let me put y is equal to s. Then what happened? Then, if x to s is proper, smooth, then this is isomorphic to this, but Let's consider the constant Hughes. Then the left-hand side is the cohomology of the special fiber of this one, and this is isomorphic to the. Oh, sorry, I missed. Yeah, so so R psi M is isomorphic to, so the direction is inverse. So M is isomorphic to R psi M, where M is an abelian group. And we consider it as a constant Hughes. Oh yes, so it is V over NZ module, and we regard it as constant Hughes. Then the nearby cycle of constant Hughes is isomorphic to the constant Hughes if X is smooth. So it means that if X has good reaction in some sense, then nearby cycle is trivial in some sense. So the nearby cycle reflects the singularity of reduction of this family. Okay, and by putting 2 and 3 together, by 2 and 3. So assume that F from X to S proper and smooth. Then what happened? So in this case, R psi M F is equal to M, and this is again M. So R gamma X S M is isomorphic to R gamma X is bar M. So the cohomology of the generic fiber is isomorphic to the cohomology of special fiber. So it is a very simple. So this is mod P reduction. So this is simpler than the cohomology of generic fiber. So the variety has good reduction over S, then the special fiber and the generic fiber have the same cohomology. This is a very important tool to study the Himura variety by using mod P reduction and counting points. Okay, are there any questions?
Do we know that the homology of Adic space is bounded above?
Oh, yes. Yes, under some condition we know it. It is bounded by the 2 times the dimension. Oh. This is the end of my explanation on the classical or scheme theoretic nearby cycle. And let me pass to the formal nearby cycle. So what is the formal nearby cycle? So let X be a formal scheme over spoof V. And I want to construct I want to construct nearby cycle functor for this X. R psi for X. We can just imitate the construction for schemes because we have generic fiber of this X. So recall that. So we have the generic fiber. this is a rigid generic fiber of this x, and we put tx eta bar to be tx, taking base change from this to super k bar v bar. And v bar is a variation ring of k bar, namely the integral closure of v in k bar. This is, so then we have an analogous commutative diagram of sites. So x red at 2 x at 2 x eta at eta at. This is a diagram of sites. There are so many geometric objects in this diagram. This x red is a scheme, and this x is a formal scheme, and tx eta and tx eta bar is an adic spaces. Yes, okay. And we know that the etale site of x red and the etale site of x is isomorphic. This is because etalemorphism extends infinitesimally automatically. And what is this lambda? This lambda is a very simple functor. So morphism of sites means that we have a pullback of object, namely open subset or etalemorphism on this site to this site. So we have only to define pullback. So assume that y to x is etale, namely this is an object on this site. Then we can attach a morphism of adic space ty eta to tx eta, and it is easy to observe that it is etale, and this is the definition of this lambda. Oh, actually we should observe that if y alpha to y is a covering, then the image by this functor is also covering, but it is easy to observe. Then we can just make a similar construction. So the definition is that let f be a sheaf on tx eta et. Then put r psi, this is a capital psi, r psi x to be the pullback by I of the pushward by lambda bar of the pullback by pi of f. This is a similar construction, and we call it formal nearby cycle. Formal nearby cycle complex. Okay?
So the etale site of curly x,
Yes?
as a formal scheme, is the same as the etale site as the adic space.
So you are asking the relationship between this and this?
No, I mean, so you construct curly x as a formal
Yes?
It also has a edit space.
Oh, x and this dx.
Yes, yes.
X and this dx. Oh, yeah, I haven't considered it. Because this is not analytic. Actually, I didn't define the etaleness over this. But under proprietary definition, it should be, I'm not sure, but it has very, they are very close.
So there is no theory of cohomology for edit space, only for which there is right?
No, actually there is. But in this lecture I didn't explain. I won't explain, but yes. Probably there are equivalents. But I don't know, I'm not sure. The fan site might not be isomorphic, but the cohomology is the same.
So toposes are isomorphic.
So I'm not sure. At least the cohomology is the same. We can prove that. So So I mentioned that the cohomology of the nearby cycle, is isomorphic to the cohomology of the geometric J fiber if the X is proper over F. So we give a adic space counterpart of this result. This is this proposition. This is very simple. X red X R psi F is always isomorphic to the cohomology of the generic fiber. We don't need any assumption. This is because this morphism of sites is equivalence. So in the case of schemes, we need properness to make push forward compatible with pullback by this I. But in this case, I is equivalent. So it always commutes with push forward and pullback. And we have this proposition. So if we know this complex, then we can compute the cohomology of adic space by using the cohomology of this scheme. And we have the following comparison result on nearby cycles, the theorem. Let X be a scheme of finite type over V, and let Y be a closed subscheme of the special fiber. And put X to be the formal completion along this Y. Then we have a comparison function from. So actually we have a morphism of locally linked space. Epsilon is a morphism of locally linked space, and this epsilon induces a morphism sites Tx eta at 2 x theta at. So this gives a way to compare the cohomology, compare the sheaf on the genetic fiber of X and the rigid genetic fiber of this formal scheme. And the result, this is not a statement of the theorem, but the statement of the theorem is first, if y is equal to xs, then if y is equal to xs, then for every torsion sheaf f on x, x eta, r psi, epsilon upper star, f is isomorphic to the nearby circle of f. We can compare them. So this one is a scheme. This one is a sheaf over where? Over x red. This is over x red. Over x red. And this is over xs, as I said. And x red and xs have the same underlying topological space. So the etale size of this and this are equivalent. So we can, it makes sense. Okay? And as for general y, we should assume more. Let n be an integer which is invertible in V, and let f be constructible V over nz sheaf on x theta. Then we can compare them. R psi epsilon upper star f. So the rigid analytic nearby cycle, formal nearby cycle, is isomorphic to the restriction of the usual nearby cycle to this y. In this case, this is the sheaf over y, and this is the sheaf over x red, and x is the formal completion of x along y, so the underlying space of x red and y are the same, so we can compare them.
Question.
Yes?
Are x red and xs not isomorphic as schemes?
Sorry, what is?
xs and x red.
xs and x red? Yeah, but xs may be non-reducible. If there's some ramification. Okay. Yes. So as I said, by using this comparison theorem to compute some etale cohomology of Arctic spaces, so I will give some examples. So first, I am interested in the case where x is equal to a1 and y is the special fiber of it. Then, as I mentioned yesterday, the genetic fiber is isomorphic to D1. So we can compute the cohomology of D1. So let us do it. So what is it? What is it? As cohomology of the disk. But by using this proposition, we can compute it by formal nearby cycle. A1 special fiber, and alp psi V over NZ. Oh, well, I use this proposition and this theorem. Okay. Yes. First, by using that proposition, we have this isomorphism, and this actually isomorphic by theorem. So this is the proposition, and this is theorem. And because X is smooth over S, this is trivial, and we can conclude that A1S V over NZ, and I should assume that N is invertible in V. Then we know this cohomology, and this is V over NZ if I is equal to 0, and 0 if I is greater than or equal to 1.
So there are two different sides that you...
Yeah, so this size formal and this size. So sorry. What should I write? So this is a lowercase and this is uppercase. Okay. Yes, so this disk is a disk. So this is contractible in naive sense. So this is what we can expect. Okay. And of course, by the check spectral sequence, we can compute the cohomology of A1 K bar add V over NV. Because as I said yesterday, A1 add is increasing union of disks. And we know the cohomology of disk and the intersection of two disks are in disk. So we can compute the cohomology of it by using check spectral sequence. Yes. Next, I will give more non-trivial.
What's the result?
Yes. As you expected, it is isomorphic to this. Yes. V over NV and 0. I is equal to 0 and I is greater than 1. Later I will explain the comparison result on this. Actually generally we know that it is isomorphic to the cohomology of A1 as scheme. But to show it, we need to use such an argument. So it is necessary to prove comparison theorem.
What's the difference between these?
Sorry?
What's the difference between that?
This cannot be realized as a Reynolds fiber of the scheme a priori. The next example is, let X be a scheme spec V TS over TS minus pi. And I suppose y is equal to xs or the origin. So y is equal to 0 in XS. In this case, XS has a singularity. XS is the intersection of two affine lines, like this. So 0 is here. In this case, Tx eta is something like it. So it is interior of this one. So this is an annulus without boundary. The outer radius is 1, and inner radius is the absolute value of pi. So let us consider the cohomology of it.